Next topic is op-amp differentiators. So typically differentiator is an high pass filter. Okay, we discuss about why we are calling this as an high pass filter in the later part of the series. Okay, so as of now just take it's an high pass filter. Okay, and in the high pass filter the input stage as a capacitor. For low pass filter the input stage as a resistor. Okay, let me explain that point. Before that, let me draw the circuit for the differentiator. So the differentiator, the non-inverting terminal is grounded and the inverting terminal is connected through a feedback resistor to the output, and this is RF, and the input is fed through a capacitor. Okay, so this is the input capacitor Ci of reactance Xc. Okay, Ci is the capacitance value, whereas Xc is the reactance. Okay, Xc equal to 1 by 2 pi Fc. Okay, where F is the input frequency of the signal. So this is V of I is the input signal, and it is reference to the ground. Okay, so this is the circuit for the differentiator. Let me derive the output voltage derivation. Okay, this is as before we discussed in the integrator. The output voltage can be derived from the Kirchhoff current law. Okay, KCL law. Okay, so the input current, which is the current through the capacitor, okay, IC, cannot flow into the inputs. Okay, therefore this input cannot flow through the input, therefore the input current must be equal to the feedback current. Okay, so by KCL, Kirchhoff's current law, okay, by Kirchhoff's current law, IC equal to IF. Okay, and IF, we already know the output current is nothing but the output voltage divided by the feedback resistance. But what's the value of this current in the capacitor? Okay, we know that the charge in the capacitor is equal to C times V, right? Therefore the rate of change of charge is nothing but current, which is the current in the capacitor, which is equal to C times the rate of change of voltage across the plates of the capacitor. Okay, therefore our IC equals to dq by dt, which is equals to C dV times V times dt. Okay, and this V is nothing but the voltage is through this input signal, therefore this is Vi. So if we using this one, equation 1 and 2, using 1 and 2, we can write that V0 by RF equals to C dVi times dVi by dt. Okay, or the output voltage V0 equal to, and also I forgot to mention this output current is, here we have an inverting output, therefore the output voltage is negative voltage. Okay, therefore it's minus here, therefore we have minus Ci. Okay, this is input capacitance Ci RF times dVi by dt. Okay, so our output voltage is the derivative of the input voltage. Okay, and this is the factor of amplification. So that's why this is called a differentiator. Okay. So what's the gain of the this integrator? So if you look here, it's an inverting amplifier, and in the place of the input resistance we have the capacitive reactance, and in the place of feedback resistance we have the feedback resistor. Okay, therefore we know by inverting amplifier formula, by inverting amplifier gain formula, we know it's the feedback resistance divided by the input resistance. Okay, in our case the input resistance is the capacitive reactance. Okay, the gain, therefore the gain of the integrator is RF times RF divided by XC. Okay, where XC equal to 1 by 2 pi FC, and F is nothing but the input frequency, input signal frequency. Therefore when the frequency increases, if the frequency increases, okay, when F tends to infinity, what happens to XC? XC tends to 0. Okay, as a result, what happened to the gain? The gain tends to infinity. Okay, so infinity is nothing but the open loop gain, and we don't like open loop gain because the circuit becomes saturated. Okay, when the gain of this differentiator tends to infinity, then the output voltage is saturates to either plus VCC or minus VCC without performing the differentiation, right? So in order to reduce the gain, okay, in order to fix the gain at high frequency, okay, at high frequency, we add a series resistor in the circuit, series resistor with the input capacitor. Okay, therefore the modified circuit looks something like this. Okay, this is the first modification. There are two modifications. Let me draw the first modification. Okay, so the first modified differentiator looks something like this. So as usual, the non-inverting terminal is grounded, the inverting terminal is connected to the output through a feedback resistor, and we have a capacitor here, and for high frequency this capacitance, the reactance of this capacitance tends to 0. As the result, the whole amplifier gain tends to infinity. So we don't like that gain. We want to make the gain a large value but not infinite value. So in order to reduce that, we add a series resistor with the capacitor, right? Therefore in that way, if our input frequency is very high, right, even if the input frequency is very high, then with the addition of this input resistor, the modified gain equation looks something like so. This resistor is in series with this capacitor, so we have, and the reactance of the capacitor is C. Okay, therefore the total input impedance, okay, the total input impedance IT is nothing but root of xc square plus ri square, right? Instead of xc, let me put xi, okay? Input impedance, sorry, input reactance. Therefore this is the input reactance and this is the feedback. Therefore the gain equation becomes Rf divided by root of xi square plus ri square. Okay, so what does this do? So at very high frequency, even though this xi tends to 0, we have a finite resistor. Okay, and as a result this amplification factor does not blow up to infinity. Instead it is a large value but a finite large value, right? So this is the first modification. This modification is to make the differentiator stable at a high frequency input. Okay, so why I had Ri? So the reason is, okay, without the input impedance, without this input resistance Ri, okay, the gain of the op-amp differentiator, okay, is given by A equals to Rf divided by Xi, okay, where Xi is the impedance of this capacitor. Okay, and at very high frequency, that is when f tends to infinity, this Xi tends to 0. As a result, our A tends to infinity, or the differentiator output gets to saturation. Okay, so with saturation there won't be any differentiation action taking place. Okay, that's why we add an Ri. In that way we can reduce. So by adding Ri, okay, the gain of the op-amp now becomes Rf divided by Xi square plus Ri square root of, right? Okay, so this makes, even though this Xi tends to 0 at high frequency, this Ri remains constant. As a result, the gain of the op-amp is large but it's not finite. Okay, and therefore the differentiator does not goes to saturation. Instead it works in a below saturation point. Okay, that's the important thing. Okay, so there is another problem. If that is through the input noise, high frequency input noise. Okay, if we have, so the next thing is, let me use some other color. Okay, suppose if we have a high frequency input noise along with the input signal, so what happens to the noise? The noise get amplified, noise also get amplified at the level of A, okay, at the level of A equal to RF divided by root of xi square plus ri square, okay. In that way it distorts the output, differential output, okay. It makes the differential output makes very errory, okay. So in order to suppress that, we need to reduce the amplification factor for the noise, okay. So the amplification factor for the noise can be reduced by two ways. Either at high frequency, if the noise is at high frequency, this x input, okay, this reactance of the input capacitor is very low, okay, so it won't play any role, and this is fixed, okay. So the gain of the gain for the noise can be reduced only through reducing this RF, okay. Since there is a direct relation, the gain of the op-amp for noise can be reduced only by reducing RF, okay. If we reduce RF, we can reduce the gain, but if we reduce the RF, it also affects the gain of the signal, okay. So let me write. So to reduce the gain for the input noise, we have to reduce the feedback resistance, okay. We have to reduce the RF, okay. But reducing RF, okay, reducing RF results in reducing the output gain of the signal, okay. It also reduces the output gain of the signal, okay. So our aim is to keep the output gain of the signal at this level, but we want to reduce the gain of the op-amp for the noise to a much lower level, or to unit gain, okay. That can be done through adding a parallel resistor with parallel to RF, okay. So let me draw again the modified circuit. So the second modification, let me use some other color, let me use green color, okay. So this is second modification. So this second modification is to reduce noise gain. Reduce noise gain. So this is the final circuit. This is our RF. In parallel to this RF, we add a very low value capacitor, okay, parallel to RF, okay. I'll tell you what it will do to the feedback network, okay. And here we have the input capacitor and input resistor, and here we have our signal, okay, with respect to ground. So this is the new addition and it is called CF, okay. So with this addition of this second feedback capacitor, what it makes is when we have an input noise, okay, high frequency input noise. So this capacitance as a reactance is nothing but the resistance shown by the capacitor, okay, as a reactance given by 2 pi f noise, okay, noise, high frequency noise into CF, okay, and the reactance shown by the feedback capacitor CF is 2 pi fs, okay. This is for signal frequency. Usually the noise frequency is of the order of 10 power around 10 power 5 hertz, right, 5 or 6 hertz, okay, whereas our signal noise will be whereas the signal frequency is of order of 10 power 2 or 3 hertz, okay, or 2, usually 3 hertz. Therefore, the reactance seen by the noise is much less than the reactance seen by the signal, okay. Therefore, the reactance XF for noise is very much less than the reactance for the signal. So as a result, so for high frequency noise, so if you look at this part, okay, so what does it mean? If XF is very low, that means that the feedback network is established through this one, okay, and the resistance, okay, or the reactance is much lower, okay. So whenever the feedback reactance is very low, the gain also tends to decrease, okay, because the gain as the feedback impedance, okay, impedance to the feedback divided by impedance to the input impedance, okay, input impedance. So for high frequency noise, the impedance is very low, okay, the feedback impedance is very low. Therefore, the noise amplification is more or less unit, okay, it gets an unit amplification, whereas for the signal the order is 10 power 3 orders higher than this impedance. Therefore, for the amplitude of, this is for noise, okay, and this is for signal. So the amplitude of this input impedance for signal, okay, input impedance for feeds, the feedback impedance divided by the input impedance, okay, and this impedance is the impedance due to the signal, okay. Since this frequency is 3 orders less than the frequency of the noise, this XF is much higher than this one, okay, here we see, okay. As a result, this impedance is 3 orders higher than this impedance, okay, feedback resistance, okay. So we know that the gain of the signal is very much higher than the gain of the noise, okay. So by adding this extra low capacitance, we have reduced the gain of the noise, okay, to unit level. So with all this modification, let's examine what's the actual gain relation, okay. So the actual gain relation is feedback impedance is nothing but feedback impedance divided by input impedance. Okay, and the feedback impedance is nothing but, here in the feedback network we have a resistor and a capacitor in parallel. Okay, in parallel. So this part, okay, and this capacitor has a reactance of XF and the resistance is RF. Okay, so this is the feedback impedance. So these two are in parallel. We have to use feedback, okay, where I is the impedance, equal to, this is the feedback network's impedance, which is XF RF divided by root of XF square plus RF square, right? So what's the input impedance? For the input case, we have a resistor in series with the capacitor. Okay, and this is Xi and this is Ri. Okay, therefore the input impedance, this is also impedance. Okay, and this is the input impedance. Input impedance is the resistance seen by the input signal. Okay, this part. So since they are in series, and we can write them as Xi square plus Ri square. Therefore the new gain equation is XF RF divided by root of XF square plus RF square into, since this is in the denominator here, you have to multiply it with this factor. Okay, so Xi square plus Ri square. Okay, so let's examine the frequency response using this gain relation. Okay, at very low frequency, that is at very low frequency, we can modify this equation as follows. Okay, A equal to XF RF divided by low frequency F tends to 0, both XF also tends to infinity and Xi, okay, Xi also tends to infinity. Okay, they are not equal to infinity, but they have very high impedance. Okay, reactance. So if we substitute this here, then we cannot get any meaningful amplitude value. Okay, amplification value. So in order to apply this infinities, we have to first find the limit. Okay, so I am taking this XF here outside the square root, therefore we have XF root of 1 plus RF square divided by XF square, right? Okay, and here let it be as it is. Okay, Xi square plus Ri square. Okay, so if we now substitute this infinities here, then it becomes indeterminate, because the numerator also has an infinity, the denominator also as in infinity, so it is indeterminate. Okay, so that's why I'm taking out this xf outside, so that we can remove this xf in the numerator. Okay, so as this xf and this xf goes out, we have a equal to rf divided by root of 1 plus rf square divided by xf square into root of xi square plus ri square. Okay, now we can so these are in the limit xf comma xi tends to infinity. Okay, and here also limit xf xi tends to infinity. We not yet substituted the limit, but we just reduce the form. Now if we substitute the limit, we have rf divided by, this part is 0. Okay, so if we substitute the limit 1 plus rf square divided by infinity, then it will be 0, and we have root of infinity plus ri square, right? And this part is infinity. Okay, therefore we have 1 into infinity, therefore e equal to rf divided by infinity, which is 0. Okay, whenever there is a large value in the denominator, then the whole equation becomes 0. Therefore at a very low frequency, so this is when f tends to 0. Okay, when at very low frequency, both xf and xi are very high, therefore the gain of the differentiator is 0. Okay, at x tends to 0. Okay, this tends to 0 means the frequency is very low value. In that case, the gain of the amplifier is 0. So if we draw a frequency response diagram, okay, so we have frequency here, gain here, and this is, you have to remember this value is 1. Okay, not 0. We have 0 somewhere here. Therefore at very low frequency, okay, the gain of the amplifier is at this 0 level, and as the frequency increases, the gain starts to increase. Okay, and it reaches 1. Okay, so this is an important line. We have to derive how the gain equation is equals to 1. Okay, so for that, let me go back to this equation. Okay, so in this equation, so let me take this equation. At as the frequency increases, xf alone tends to infinity. Okay, whereas xi becomes a large value, but not infinity, but a finite value. Okay, this is because, so if we take xf equal to 1 by 2 pi f cf, right, and xi equals to 1 by 2 pi f ci. Okay, this is the capacitance of the input capacitance, and this is the capacitance of the feedback capacitor. Okay, this CF and CA are chosen in such a way that CF is way less than Ci. Okay, and since the frequency is increased, not 0 here, since Cf is very much less than Ci, this quantity, okay, this product is very much less than this product. Okay, therefore this Xf is still a very high value, whereas this Xi is somewhat in the finite range. Okay, so that can be approximated from this equation. Okay, so we know that in the limit Xi alone, Xf alone tends to infinity, we can write Xf divided by Xf Rf divided by root of Xf into 1 plus Rf square divided by Xf square into root of Xi square plus Ri square. Okay, here as the frequency is large, this product is somewhat larger than this one. Okay, as a result, this Xi won't goes to infinity. That's why I am putting only the Xf tends to infinity. And if we substitute the limit, we have this and this goes, and if we substitute the limit, this value tends to 0. Therefore we have Rf divided by root of Xi square plus Ri square. Okay, and this is the equation which governs this part. Okay, at this part A equals to, at this region A equals to, in this region A equals to 0, and this part is governed by A equals to Rf divided by root of Xi square plus Ri square. Okay, in this region, up to in this region. Let me draw in another color. Okay, and when this at this point, okay, at this point is called the F1 point. Okay, at F1, okay, at F1 frequency, what happen is Xi square plus Ri square root of this one equal to Rf. Okay, as the frequency is further increase, this Xi decreases, and at our point the sum of this reactance is equals to the feedback resistance. Okay, and still this Xf is very large. Okay, at this frequency. Therefore what we have at F1, okay, the first cutoff frequency, we have A equals to 1. Okay, equals to 1. And what's the value of this cutoff frequency? We know that at Xi equal to 1 by 2 pi Fci, right? Or Fi equals to 1 by 2 pi Xi Ci. Okay, so at this reactance, okay, this frequency Fi is given by 1 by 2 pi. Instead of this reactance, we have this reactance, right? We have root of Xi square plus Ri square. Okay, that's the reactance. And at f1 we know that this quantity is equal to RF. Okay, this xi square plus ri square equal to RF. Okay, therefore we have at f1 equal to 1 by 2 pi RF Ci. Okay, so this is one of the important relation. The first cutoff frequency, first cutoff f1 equals to 1 by 2 pi RF Ci. Okay, feedback resistance and input capacitance. So what's happened when we further reduce the frequency, further increase the frequency, and as we further increase the frequency, this Xi becomes very low. It tends to it's very low, and therefore the gain increases. Okay, increases constantly at this point at a particular frequency. Okay, this Xi, okay, becomes 0. Okay, this Xi becomes 0, therefore, okay, let me another frequency, this f0 point. Okay, at f0 Xi equals to 0, therefore we have, therefore our A equals to RF divided by Ri. Okay, we have root and the square are get cancelled, therefore we have RF by Ri. And further increasing the frequency, the gain remains constant up to certain point, and here we have the gain equals to A equals to RF by Ri. Okay, so at this point, at this frequency, let me write as fxf. Okay, because at this frequency the xf is no more infinity, it starts to show, it starts to become very low value. Okay, it's not become, won't be a high value, it starts to reduce. Okay, for very large frequency it starts to reduce. So let me write it here. At f0 Xi equals to 0, therefore our A equals to RF divided by root of 0 plus Ri square, which is equal to RF by Ri, right? And further increasing the frequency, and at f equal to f of xf, okay, this approximation is no more valid. Okay, this approximation is no more valid. Okay, because xf is starts to get very low. Okay, and at that point the amplitude is given by, okay, the amplitude is xf, our original amplitude equation, this one. Okay, this one, okay, this equation. But this part is gone, okay. So I have to rewrite at this frequency XF is very much less than RF, okay, and we also know this Xi is already equals to 0. Therefore our equation becomes A equals to XF RF divided by, instead of taking XF from the root, now we take the RF outside, okay, RF outside plus 1, okay, into root of, already Xi equals to 0, we have Ri square. So this RF and RF goes out, so we left with XF divided by root of XF square divided by RF square plus 1 into Ri. So further increasing the frequency, beyond this frequency, the amplitude, this XF tends to get lower and lower. As a result, this amplitude also gets lower and lower. Therefore, if we look at this part, it starts to decline, okay, it starts to decline, and at one point it reaches this frequency. This is the second cutoff frequency, okay, at F2 XF is very much less than RF, therefore this term becomes 0, okay, or it can be neglected, okay, and the XF equal to Ri. At F2 XF equals to Ri, okay, therefore, so if we neglect this part, okay, we have A equal to XF divided by Ri, and at F2 this XF is also equal to Ri, therefore A becomes 1 again. Okay, that's why in the graph it starts to decline. It starts to decline and reaches the unit gain value here, okay, at F2. So what's the frequency? Therefore F2 is given by 1 by 2 pi Ri CF, okay. This is the second cutoff frequency. So in order to have a faithful differentiation, the accuracy of good accuracy, we need to operate between these two frequencies. So let me summarize what's going on here in the frequency diagram, okay. Let me put it in another understandable way. Okay. So we have our let me redraw in another way so you can understand it in a better manner. I have redrawn our original diagram. This is not a different one, but just I rearranged the resistance and capacitors. Okay. So at very low frequency, okay, this is more or less an open circuit. Okay, therefore no signals, no input signals is fed into the op-amp. As a result, the gain is 0. Okay, gain is 0 at f equal to 0. Okay, and as the frequency increases, this xi starts to conduct. Okay, xi tends to decrease, but xf is very large. Okay, xf is so infinity. Okay, therefore at that stage and as the frequency is further increased, this A becomes, the amplitude becomes, this xi is completely conductive, therefore it's a direct connection. Okay, therefore, and this is an open circuit. Okay, and with further increase in frequency, xi equals to 0. Okay, there is no gap, it is directly connected, and still xf is very large value. Okay, very large value, and at that case A equals to this is directly connected and it is open, therefore this part is, there is no this part, it is directly connected, and if it is open, the feedback is through RF, therefore the amplifier's gain is just RF times Ri. Okay, RF times Ri. Okay, that's why we put the flat part as RF by Ri. And as we further increase the frequency for very large frequencies, this xi is 0 and xf equals to RF. Okay, sorry, xf also is very much less than RF. Okay, so most of the conduction is through this network. Okay, not through RF. So since this is the least resistive part, because xf is very much less than RF, so most of the feedback is through xf. Okay. And at a certain point, this xf is also equals to this Ri. Okay, and at that point the gain is again 1. Okay, the gain becomes 1. So there are at 2 points gain becomes 1. So that's what here happening. So with this we conclude the differentiators. I think this is enough for differentiators. Okay, in the next video I will talk about op-amp comparators. Thank you.